Hello, today we're going to learn how to compute statistics relating to a government public opinion poll. In this example, we are going to actually calculate, we're going to use a public opinion poll to analyze sample public opinion where students were asked to rate their opinion of the current president of the United States on a scale between 1 and 9. So they choose 1, 2, 5, 6, 7, or 9. And we're going to calculate the confidence with which we can predict the next person that we poll, that we're going to compute a number that will tell us to some degree of accuracy the probability that the next person we ask, what do you think of the current president? We will compute the probability and the range of their answers. It's actually a fairly powerful tool, and it's not only applicable to government opinion polling, but it could also be applicable to almost anything where you need to predict the future or need to know the range of your probability given certain criteria. I know all of that sounds a bit theoretical, but there's actually a wonderful statistical metric that is not difficult to compute but seems challenging at first, and that is the standard deviation. So in this tutorial, you will learn how to compute public opinion polling statistics using the standard deviation. And then at the end, we will interpret the standard deviation so you kind of know what it is you've calculated. And I'll even try to show it in Microsoft Excel how this can be computed very easily. But first, we have to learn how to do it by hand. So let's get started. Go the deck here. We have a worksheet that will be available in the link description that it's called the Public Opinion Poll Statistics Quiz. And this is what you did in class. You are given on the left side of the page a whole list of numbers. And I'm going to turn the page sideways so viewers can see the whole list. You're given this list of numbers, and all of them fall inclusively between 1 and 9. This is actual student data taken from an opinion poll conducted in class. So what we need to find out is how these data are related to one another, and whether using this data, whether we can make any predictions about the future polling results. Does this data give us any kind of accurate measurement? Can we turn this data, in other words, into a tool for predicting future polling results? You could see how this could be useful for a presidential campaign, kind of have an idea of where the public opinion is going, or how strong your statistics are. All of this will become clear as we work through this. So for the purposes of this tutorial, we'll skip name, date, and period, and we'll just begin looking at this series of steps. This is a series of 7 steps to compute the standard deviation, and then numbers 8, 9, and 10 are explanatory questions. All right, there are a number of new vocabulary terms when we're computing the standard deviation, and the first one is population size. Population size. This is not a difficult concept. It's represented by the letter n, lowercase n, and when it says population size n equals blank, what do you put? Well, the way you find that is you go and count the number of polling results that you just count them up. So I'll turn the page sideways so the video can see it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 1, 20, 23. So I have 23 poll answers. So the total population size, the number of people I asked on a scale of 1 to 9 inclusive, what do you think of the current president of the United States? I have 23 answers. So the answer to number 1 is 23. That's n, right? The next thing is population mean, right? And it's difficult to see on the video, but what's being represented there is an X with a line over it. This is called X bar. It's also the population mean. Another way that this is often written is the Greek letter mu x, like that, mu x. So it's either x bar or mu x. For purposes of this demonstration, we're going to compute the population mean as opposed to the sample mean. We'll get to sample in a later tutorial, but right now, what I'm saying is I'm going to take all of these numbers that I have, I'm going to add them up and divide by n. Well, in this case, n is 23, so I'm going to add up all of my poll results and divide by n. Now, this should seem familiar to most people because all I'm really computing is the simple average of these numbers. But I don't want to write average here because we're dealing with statistics, and average is a confusing term. It becomes very ambiguous when you're talking about statistics. So we're going to say population mean represented by x bar or mu x, whatever your preference is. Just remember that these two things are the same thing. And we will then add up all of our results and divide by n. So you can see it. I'm going to perform it right now. All you need is a basic 4-function calculator. I keep saying 4-function, but you actually need 5th function, I suppose. You need the square root function on your calculator. You can also use your phone or type SQRT and then the number into Google, and it will automatically compute the square root. But anyway, let's do step 2 here, which is the population mean. So I'll take 6 plus 2 plus 6 plus 8 plus 9 plus 4 plus 5 plus 2 plus 3 plus 5 plus 7 plus 6 plus 8 plus 1 plus 1 plus 2 plus 5 plus 5 plus 6 plus 4 plus 3 plus 9 plus 8. And I get a sum of 115. Well, let's just hang on to that number for now. We'll put down here uppercase sigma, which equals sum, which means sum. That equals 115. We don't need that really, but we'll keep it there in case we forget or our calculator dies on us or we have to come back to the problem later. Now I'm going to take, so the population mean is equal to the sum of the answers given divided by n. So my population mean is 115, okay, divided by n, or 23. So 115 divided by 20. What does that equal? Well, that equals x bar or mu x. And mu, if I should indicate this, mu, this Greek letter mu, is spelled it's phonetically how it sounds, mu. And what it means is the population mean, or the mean. So let's take 115 divided by 23, and we get 5. So in this case, the population mean is equal to 5 right here. Right, so that's actually number 2. It's 5. Number 3, what's that? What is it asking us to do? Number 3. It says let's compute the differences from the mean. It says there x minus x bar. Okay. Now that remember, I could also write that x minus 2x. Same thing. X minus x bar, x minus mu x. I'm really saying take x and subtract out the population mean. Okay. Well, many students ask, what do I do with x? What does that mean? What is indicated by x? Well, each value here is x. Okay. So when I say x minus x bar, I'm going to call all of these values x, and from each value, I will subtract out x bar. And x bar population mean is 5. So for every answer that I have, every poll result, I'm going to subtract out 5. So I'll put x minus x bar. And then in this column, helps to make a table or column. On this worksheet, we can just kind of fake it. We're going to make a column for x minus x bar, and that'll be each result I get, I'll put right next to the number. This is actually pretty simple. We don't even need a calculator. The population mean was 5. So the first result is 6. 6 is x. X bar is 5. So 6 minus 5 is 1. So that first answer is 1. 2 minus 5 is negative 3. 6 minus 5 is 1. 8 minus 5 is 3. 9 minus 5 is 4. 4 minus 5 is negative. 5 minus 5 is 0. Minus 5 is negative. 3 minus 5 is negative 2. 5 minus 5 is 0. 7 minus 5 is 6 minus 5 is 1. 8 minus 5 is 3. 1 minus 5 is negative 4. 1 minus 5 is negative. 2 minus 5 is negative. 5 minus 5 is 0. 5 minus 5 is 0. 6 minus 5 is 1. 4 minus 5 is negative. 3 minus 5 is negative 2. 9 minus 5 is 4. And 8 minus 5 is 3. All in there. So now I've got this another set of numbers. And it says here, differences from the mean. Then it just says check when done. Well, we did. We computed the differences from the mean and we listed them next to our original values. So these represent the differences from the mean. Now, before we continue, I think it would be helpful. Certainly, it couldn't hurt to show visually what it is that I'm actually doing with all. Let's take a look at a depiction of this information graphically. I think I can set this up best by turning this paper like this. Then I'll draw what I'm doing. What am I coming up with? X minus X bar, or X minus the population mean. Okay, I'm coming up with something that looks like this. So I'll draw a line here and a line here. On this centered, right here, we're going to call this X bar. Okay, that's equal to 5. Now, if that's equal to 5, we'll call this 6, 7, 8, 9. Then underneath 5, we'll go 4, 3, 1. 5, 6, 7, 9. Now, what we'll do is we know we have 23 results, right? We're actually going to plot all of them. I want you to see this so you know what's going on. So I'll try to use my ruler here, make each plot the same distance. This one. $17. So there I'll have plotted 23 results. So let's take a look at a few of them. For this, I'll use a blue pen and a red pen to make it stand out. My blue pen will be actual value, right? So the first value gives 6. Where is 6? 6 is right here. So 6 is right there. That's 6. Now, when I say x minus x mean, it says take 6 and subtract out the mean. So what I'm really asking for is, what is the distance between 6 and the mean? What is that distance there? Little tiny distance. Well, that's just 1. As you see, x minus x mean is 1. So if I was making a table above this, I would put 1. So that's the x minus x mean value there. Okay. I see that this is getting a little hard to read. Let me improvise this here. Just a moment. It's bigger. We'll make a dark line. I really want you to see this, and I don't want the values to be so it's darker. I'll replot the so see just one more. So we'll leave that one. Then I'll call this 3, 6, 7, 16, 17. I've really just given myself more room to work. Let's continue. So my first value was 6, and the x minus x bar there was 1. So what's my next value? My next value is 2. So let's actually plot 2 and go down here. Starting here, we'll go down to 2. Plot down to 2. So there's 2. That will be my second poll result right there. 2. See, so I've got 2. There's the poll result. What is the distance between the poll result and the mean? Well, x minus x bar is 2 minus 5. So the distance is actually minus 3. That's x minus x bar. The next value is 1, which we already computed. So I'll just put 1. We know that our x minus x bar value there is 1. My next value is 6, 8. So I need to plot 8, right? Go over here to 8. We're going to be on our third value now, or fourth value rather. So we'll go on 8 over to fourth value marker. I'll plot that point right there. So this is 8. It's a poll result. What we're going to find is the distance between value, which in this case, if that's 8, the mean value is 5, that distance is 3. Okay, I'll do a couple of more of these and then move on because I think you understand what's going on. What's my next value in the sequence? 6, 2, 6, 8, 9. So my next value in the sequence is 9. We'll go up to 9, move over to our next placeholder, make a placeholder. That's the 9 value, 9 poll result right there. And we'll find the distance between that value and the mean, dot, 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 down to mean. So in this case, 9 is the x value. Population mean is 5, so 9 minus 5 is 4. So we'll just put a 4 right there. See how that is in sync with our 4. we could proceed for the full 23 values. Would see how the information was distributed around the might actually be worth doing, but I want to keep this video at certain practical length. Anyone wants to see this, just continue doing this. I guess I'll do just one more to make sure you understand completely. Next value is 4. So take your ruler if you have one, and you're going to be looking at this point here, the next poll result, put it on 4, and put a little dot beneath the value right there. So there's your poll result 4. What is the distance between 4 population mean? Well, the distances go from 4 minus 5. Well, that's negative 1 distance. This is the x minus x bar interpreted visually. I hope that gave you at least a visual understanding of what that step indicates that you should do. I highly encourage you to that process for all 23 values, because it will teach you what x minus x bar literally means or visually means. Okay, now the next step tells us to find the squares of the differences from the mean. So the squares of the differences from the mean. Oh boy. Well, it says here x minus x bar squared. What it's asking us to do is x minus x bar, then square the value. Looks scary, but we've already got the part inside the parentheses because we did that in step 3. Differences from the mean. That's all that is, x minus x bar squared. So these are my x minus x bar values right here. I can just create another column. This time I'll do it in, I guess, blue. And I'll use this line as my column line. Just bring this guy out here. Say x minus x bar squared. We'll put all those values. How am I going to do that? I just square, again, for this example, you don't need a calculator. What is 1 squared? That's just 1. Whenever you square a negative number, it becomes positive. So what is negative 3 squared? That's 9. 1 squared is 1. 3 squared is 9. 4 squared is 16. Negative 1 squared is 1. 0 squared. All right, so a lot of people have questions about 0 squared. 0 times 0 is 0. All right, so 0 squared is 0. Negative 3 squared is 9. Negative 2 squared is 4. 0 squared is 0. 2 squared is 4. 1 squared is 1. 3 squared is 9. 4 squared is 16. Negative 4 squared is 16. Negative 4 squared is 16. Negative 3 squared is 9. 0 squared is 0. 0 squared is 0. 1 squared is 1. Negative 1 squared is negative 2 squared is 4 squared is 9. And 3 squared is 9. Okay? All the values. It says here, the squares of the differences from the mean, check when done. Well, we did it. So let's check the box. We're done. Now on to number 5. It says here, the sum of the squares of the differences from the mean. Sum of, that's that uppercase sigma, the sum of, whenever, I always tell the student, you see this symbol, this uppercase, scary looking, robotic looking, this is an uppercase sigma. whenever you see that symbol, it's kind of like it's saying, little thought bubble, saying, add me up. So it's saying anything to the right of me, add me up. Or whenever you see this symbol, add up the things above it. It says the sum of. You can literally read this as the sum of. But I kind of like to think it's add me up. So it says here the sum of, here's sum of, that's the sigma symbol. Sum of the squares of the differences from the mean. That's represented by x minus x bar squared. The sum of x minus x bar squared. Well, again, if you just look at this here, it can look kind of scary. It's like, oh my goodness, that's too much. But you've already done x minus x bar, that in number 3. Then you did x minus x bar squared in number 4. So now all it's saying is add up values you got in number 4. Really, number 5, the sum of the squares of the differences from the mean. Oh, sigma x minus x bar squared. Oh boy. Well, all that means is take all these blue numbers here that I've got and add them all up. Now, you don't really need a calculator for this, but it makes life easier. So we'll just take 1 plus 9 plus 1 plus 9 plus 16 plus 1 plus 0 plus 9 plus 4 plus 0 plus 4 plus 1 plus 9 plus 16 plus 16 plus 9 plus 0 plus 0 plus 1 plus 1 plus 4 plus 9 plus 9. It's 129. Okay. So down here, I've got my sum of. Down here, my sum is 129. 129. That's 1. Let's go back up to number 5. What did it ask us for? The sum of the squares of the differences from the. That's exactly what we found. 129. 120. That was equal to sum of squared differences from the x minus x bar squared. That's what that means. Now, number 6, we've arrived at an actual statistical calculation that's useful. This thing called the variance, or sigma squared. This is the Greek letter sigma. Okay, it kind of looks like a 6 that's fallen over or a 9 that's fallen over. Greek letter sigma squared. Sigma, S-I-G-M, sigma squared. And what this is equal to is the sum of the squares of the differences from the mean for x bar divided by n. Let's write that out. Now we know what sum of, that's the symbol sigma, so we'll just write sum of, right, sigma, sum of the squares of the differences from the mean, sum of the squares of the differences from the mean. Then it says divided by n. That's what it's asking us to do. So we know n from number 1 is 23. And we found the sum of the squared differences from the mean in number 5. I mean, read number 5. The sum of the squares of the differences from the mean. So we've got this part here, the numerator. We've got the denominator, division problem. So got this number. This is 129. 129 divided by, and what is n? If I got to number 1, population size n equals 9 divided by whatever that equals is the variance, sigma squared. So just follow along with the logic. Divided by 20 equals 5.608. We'll take it out. We'll make it 3 significant digits, so 5.61. 5.61. Now we need to square that value. So squared. Oh, I'm sorry, we make a mistake here. We don't square that value. Wait, ixnay with the aired square. Just some little magic marker erasures. Okay, so 129 divided by 23. Got a little ahead of myself. Is 5.61. So the variance in this set of data is 5.61. That there, right? Now the standard deviation is merely the square root of the variance. Standard deviation is just sigma. So is it any surprise if standard deviation is sigma, that is equal to the square root of the variance. Another way to write that is the square root, remember the variance is sigma squared, is sigma squared. Square root is sigma squared. So what is sigma squared? It's 5.61. So the square root of sigma squared is the square root of 5.61. That will be equal to the standard deviation. We're going to talk about what that means, but let's take 5.61. Then if I hit this little square root sign, it'll get the square root. 2.368, 3 significant digits, 2.39. It's 2. So the standard deviation from the mean is 2.39. That's the answer. That's sigma, standard deviation, 2.39 in these poll results. But we really, if you've gotten this far, let's first give a little golf clap, okay, and let's see what you actually calculated. So let me now, before we explain what we're talking about, you need to give yourself a round of applause because you actually did something quite significant. Calculated this formula. Sigma equals, like a big radical sign here. It's fun to draw this. Sigma equals square root of the sum of the squared differences from the mean divided by n. That is the formula for standard deviation. Standard deviation. At this point, if you're watching this video and you're knowledgeable about statistics, this is called the population standard deviation. But for my students, for now, this is the standard deviation equation. But if I had shown you this equation to start, and said compute it, be daunting and scary. But if you break out this equation to its little components, see none of it was very hard. And when you're done, you have this cool looking equation. It kind of looks to me like Einstein's equation or something. Got a lot of cool Greek letters and it's neat. And that answer was 2.9. but we really don't know much yet. What does this mean? How do I interpret that? What information does that give? Let's take a look at what, incidentally, we did number 10. Write out the equation for standard deviation using mathematical operators. That's what this is, right? This is number 10. Playing the home game and doing this quiz, that's number 10. Okay, explain in your own words what the standard deviation means. Let's use a different piece of paper, because I want to explain this to you. To explain standard deviation, we have to introduce something called the bell curve. And it's named the bell curve because it looks like, drum roll, a bell. Let's take a bell curve. You do this as you a vertical line and then a horizontal line. And you want to draw this shape. It's actually kind of hard to draw correctly. What I'm about to draw will be highly inaccurate. Looks kind of like this. And it's supposed to be symmetric about the center. As you can see, I didn't perfectly reflect that. It's a terrible artist. But you understand it's supposed to be a bell. Now, in the bell curve, this center value right here is the mean, x bar. So when I calculate standard deviation, I'm calculating standard deviation from the mean. And you can kind of see a hint of what I'm doing with this plot right here. What I'm saying is, how many of the values, what percentage of the values in my poll lie within a standard deviation of the mean? Well, we'll plot 3 standard deviations on this bell curve, and I'll explain everything. So we're going to split each side of our bell curve into 3 equal parts. First, let's just and what we'll do is we'll put a dotted line. That's representing 1 standard deviation. And my dotted line here, standard deviation. And then, so I need a final point, standard, 3 standard deviations. Same thing on the other side. Standard deviation, standard deviation, standard deviation. Notice that that third standard deviation, there's still a little tail coming off the end of the bell curve that's not accounted for. But I'll write in that this is 1 standard deviation, or 1 sigma. This is 2 standard deviation, or sigma. This is 3 standard deviation, or sigma. Again, on the other side, 1 sigma, 2 sigma, and 3 sigma. Now, what does it mean? Again, you have to keep asking. You got to ask your teacher or yourself, what does it mean? Well, according to, like, if we think about this, where is most of the area of this curve, this bell? Most of the area is contained here in the bulbous part of the bell between my fingers, right? So within 1 standard deviation in either direction of the mean, looks like a lot of the area is accounted for. And as a matter of fact, it is quite a bit of the area. In fact, the exact value, or approximation, I should say, is that within 1 standard deviation of the mean, 34.1% of all the values are accounted for. Realize you can't actually read 34. There's also 34.1% accounted for on the other side as well. So 34.1 to the left, 34.1 to the right. Within 2 standard deviations of the mean, that adds on an additional 13.6%. 13.6%. Second standard deviation, 13.6%. Second standard deviation. Then finally, that third standard deviation gives us 2.1%. Write it in. So let me make a little table here. One standard deviation gives us 34.1% of the data. I'll explain what this means. 2 standard deviations, second standard deviation gives us 13.6%. The third standard deviation gives us 0.1%. This isn't very useful because I still don't really know what's going on. I mean, in my own mind, I'm still confused. Still don't quite understand. Well, what it's saying is that within one standard deviation of the mean, in this case, in this instance, it would be helpful to have the standard deviation kind of at the ready. That standard deviation was 2.39. Let's put some real numbers down. The mean of the population was 5. One standard deviation to the left would be minus 2.39, minus 0.39, and one standard deviation to the right would be plus 2.3. Okay, so what it's saying is that if you add up a standard deviation to the left and a standard deviation to the right, you get 34.1 times 2. 68.2% of the data falls within one standard deviation on either side of the mean. This whole area here, accounts for 68% of those poll results lie within one standard deviation to the left or one standard deviation to the right. Okay, so what does that really mean? Well, let's go back to our poll numbers. They were 6, 2, 6, 8, 9, 4, 5, 2, 3, 5, 7, 6, 8, 1, 1, 2, 5, 5, 6, 4, 3. And I started to plot them here. And what it means is within up 2.39 and down 2.39, I will have 68% of my poll answers will fall within that range. Okay. So let's actually compute what that range is. I know that 5 minus 2.39 is 2.61. Okay, so on the low end, I've got 2.61. This could be 61. Right? And on the high end, I've got 5 plus 2.39, 7.39. 7. So let me put this into an English sentence for you. If standard deviation is 2.39, okay, then 68 0.2% of data fall within the range two 0.61 to 7.39. So that's actually like a claim that we can make based on the statistics that we calculated. That's pretty cool. That's pretty cool. So that would, let me just write this out again. If one standard deviation is equal to 34.1% of the, multiplied by 2, get 68.2%. Okay. So the second standard deviation, the way that this really becomes useful is within 2 standard deviations of the mean. Add in that 13.6, so 13.6% times 2. 13.6 times 2 is 27.2, 7%. So if I'm adding in this second standard deviation here, either side of the mean, that's this extra area here now that I'm adding in 2 standard deviations. Well, you find out how much data is accounted for by that is you actually add this whole area now between my fingers. This whole area is 68.2% plus 27.2%. That equals 95.4%. So this first standard deviation accounted for 68.2%. The second standard deviation, the total area, accounts for 95.4%. So how about the third standard deviation? So the third standard deviation is equal to 2.1% times 2 equals 4.2%. Now if we add that, running out of highlighters, but I do have green, this one. If I add in the third standard deviation, you really should be doing this yourself. Now, the area between my fingers now looks almost like the bell curve. So we expect that most of the area now is included. So within 3 standard deviations, I've got 95.4 plus 4.2, 99.6. So that accounts for 99.6% of the data. This has actually got a name. This rule, it's called the 68, 95, 99.7 rule. It means that within 1 standard deviation, you're accounting for 68% of the data. Within 2 standard deviations, you're accounting for 95% of the data. Within 3 standard deviations, you're accounting for 99.7% of the data. Right? Now, you see we're accounting for 99.7 within 3 standard deviations. We can really stop there because it will really go on infinitely. These points just trail off into the distance. So let's just finish out our analysis so you understand what you're doing. We'll start a second piece of analysis here. Say, if standard deviation is 2.39, so that's all the same, ditto. then 95.4% of data fall within the range. Okay, well, this is two standard deviations. So remember, one standard deviation is 2.39. Our calculation, 0.39. So what's two standard deviations? Well, that's 2.39 times 2, 4.78. So what you'll need to do is subtract this and add this to the mean. Mean is 5. So 5 minus 4.78 is 0.22. So this number right here at the second standard deviation mark is 0.22. The left side of the mean. And on the right side of the mean, it's 2.39 times 2. That's two standard deviations. 4.78 is 2 deviations. So now add that to 5. 9.78. Okay. 9.78. We can stop here because our range is only 1 to 9. That's the poll results. We're only allowed 1 to 9. So we'll say all of the data is going to be here within two standard deviations of the mean. So that's 0.22, 9.78. We'll say if the standard deviation is 2.39, then 95.4% of data fall within the range 0.22 to 9.78. So that's how you would say that. All right, so what is, in our own words, what the standard deviation means? The standard deviation is a measure of how close the data are to the mean, how they deviate from the mean in a standard way. So how can I say that in a way that's useful? Well, this is in your own words, so I'll use my own word. I'll say that the standard deviation means that I'll say that a lower standard deviation indicates tighter poll results. So in this case, if the standard deviation is 2.39, all right, standard deviation, and I'll represent it STDev, standard deviation is 2.39, then 68.2% of data fall within the range 2.61, 7.39. Well, here's my question. You can come up with your own explanation. That's my explanation. Here's the question. Does the data set give us good predictive value? Now, guys, this is really the meat of the whole exercise. Good predictive value. Now, another way of saying this is this useful as a tool? How can I use this? If your data set is giving you a standard deviation of 2.39, and we see that according to bell curve, that range is the poll result that we know that 68% of our poll results fall within 2.61 and 7.39. Well, ladies and gentlemen, the poll scale is 1 to 9. So I've got a range of 2.6 to 7.3 with one standard deviation. That's actually fairly large. I'll say, because the standard deviation, or sigma, is so large compared to the mean, which is 5, then this data set does not offer good predictive value. So I answered both the, does the data set give us good predictive value, why or why not? I gave, it does not offer good predictive value because sigma is so large compared to the mean. Sigma is 2.39 and the mean was 5. So sigma's, almost half the size of the mean. So it's just on this, according to this bell curve, it's just the sigma is too large for us to really use it as a prediction tool. Now let me give you the alternate case. What if sigma was 0.1? Okay, or let's just say sigma was 1 for kicks. Sigma is 1. If sigma is 1, then within one standard deviation of the mean, I know that I have a 68% chance of the poll result being 5 minus 1 or 4, 5 plus 1 to 6. So I can say I've got a 68% chance with a standard deviation of 1, a 68% chance of the poll result falling within 4 to 6. That's actually very good as a predictive tool. So a standard deviation of 1 would give us a better predictive tool. A standard deviation of 0.1 would be even tighter. Okay, so that would be 5 minus 0.1 or 4.9, 5 plus 0.1 or 5.1. So you could almost know to a dead certainty that 68% of the data will fall between 4.9 and 5.1. That's a nearly perfect correlation of data. So that the smaller the standard deviation, let me add this little addendum here. This is important. Like if this is all you learn from this whole video, this is the thing to learn. The smaller the standard deviation, the better its predictive or explanatory power. So if we're really going to be reductionist about this, we could say big, bad, small, good. So I'm actually going to write that. Big sigma is bad. Small sigma is good. Okay, big, bad, small, good. That's really all you learn from this whole hour-long tutorial. Then I submit to you that you have in fact learned something fairly important. That would make me very happy if everybody in the class knows that big sigma is bad and small sigma is good. I can work with you. So I hope this has been a helpful tutorial. We have learned about the bell curve. We've learned how to compute the standard deviation. And we actually learned how to find the population standard deviation, sigma, equals the square root of the sum of the squared differences from the mean divided by the population size. And we saw that a big sigma is bad because according to the bell curve, it doesn't give us much predictive value. And a small sigma is good because regardless of the sigma itself, if the sigma is 0.1, one standard deviation still explains 68% of the data or accounts for it. 68% of the poll results fall within 0.1 of the mean if the standard deviation is 0.1. If the standard deviation is 1, that means that 68% of the data fall within one standard deviation of the mean, or 4 to 6. But in our case, the standard deviation was 2.39, so it says that 68% of the data fall within one standard deviation of the mean, which means 68% of the data fall within 2.61 and 7.39. And that is not very useful as a tool. It means that there's quite a large variance in the data. We saw, we calculated variance here and said variance was 5.61. That's a pretty big variance when your data set is only 1 through 9. So we'll end it there. Here are the two kind of major things you learned. You learned about the bell curve and you learned about standard deviation. And thank you very much for your attention. Please like and subscribe. And thanks for watching.